Welcome to the 7th lecture of probability for machine learning series, in which today we are going to cover Poisson distribution. So let's start the lecture. But before starting the lecture, I want to give you a scenario. Okay. For example, you use an Uber, right? It is not example, you must be using an Uber, right? Uber platform. Let's say Uber has a mechanism in which it can receive only one request in 1 second, right? We are taking this as a, you can say, as a case study, right? So this is the time frame 60 second slash 1 minute. Okay. So Uber can receive only one request in a minute. Okay. Yeah. So I have drawn the time frame. And in average, it is observed that the Uber platform receives two requests in 1 minute, right? Two requests. Let's say this highlighted parts. Two requests in 1 minute. Okay. So let's say we denote average by lambda. So it is 2 because it is receiving two requests in 1 minute, right? So what will be the probability that the Uber platform will receive 5 requests in a minute? Okay. What will be the probability that our Uber platform receive 5 requests per minute? Okay. So in the previous lecture, we have discussed the binomial theorem. So we are going to use that in this part. So what is the value of n here? N is the total number of events or sample space, which is 60 here. Okay. What is the value of k? K is the number of successful events. So we have to find 5 successful events. It means 5 requests in 1 minute. So k will be 5. So we are just simply writing the formula nck p raised to the power k 1 minus p raised to the power n minus k, right? So let's plug in the values. N is 60, c, k is 5, p, what is the value of p here? Okay, so we don't know the value of p here, but we know the average number of outcomes, okay, which is 2. Okay, which is 2. And what are the total number of outcomes, which is 60? Voila, we have calculated the value of p. What was the value of k here? K was 5, and 1 minus p is simply 1 minus 2 upon 60 upon n minus k. What is n minus k? It is 55. So this is a pretty reasonable equation that can be solved, right? Very easily it can be solved. But let me show you another scenario of this particular question only. Again, this is the let me draw it a little bit small. Again, this is the, you can say, the time frame. Okay, but now we have updated our Uber servers, and now it can receive every request in 1 millisecond. Okay, so it can receive different requests in 1 millisecond. Here the Uber platform was compatible to receive only one request in 1 second. Here the Uber platform can receive one request, or let me write it a little bit neatly, one request in 1 millisecond. Okay, so now in how many parts our time frame will be divided? 60 multiplied by 1000, which is equal to 60,000, because 1 second is equal to 10 raised to the power 3 milliseconds, right? So 60 seconds will be equal to 60 multiplied by 10 raised to the power 3, which is 60,000. So our time frame will here be small, and it will be divided into 60,000 different parts. And again, the lambda is same here. The average request received per minute, not per second, per minute, is 2. Yeah, and now we have to find the probability of 5 requests received in 1 minute. Okay, so again we can use our binomial theorem here, but the calculations will be very difficult. Let me write the equation at least. So what is n here? Now n earlier was 60. Okay, but now the n is 60,000. 60,000. What is the value of k here? The value of k is again the same. I think so. Yeah, the value of k is same, which is 5. The value of p we will calculate later. Okay, so what is the value of n? No, first let's write the formula. nck multiplied by probability p raised to the power k multiplied by 1 minus p raised to the power n minus k. Now let's put the values, which is equal to, what is the value of n? It is 60,000. Let me just, yeah, it is 60,000. 1 2 3 4 ones, tens, 100,000, 10,000, sorry for that. And what is the value of k? 5 multiplied by p. What is the value of p here? Now there are 2 requests received in 1 minute, but now our data frame is divided into 60,000 pieces. Okay, and so the probability will be 2 upon 60,000 here. So 60 into 10, let me just write 60 into 10 raised to the power 3 raised to the power k, which is 5, multiplied by 1 minus p, 2 by 60 into 10 raised to the power 3 multiplied by 55. Now you can see the computations are getting a little bit difficult here. Okay, let the box be slanted here, but the computations here, the amount of calculations you have to perform to go to get a desired result is very high. Okay, if I give you another case scenario similar, in which the time frames are infinite, it means that Uber can receive infinite number of requests in 1 second. Okay, so the number of time frames will be infinite. It is very difficult to draw. So here probability x is equal to 5. Again we have to find 5 requests, probability of 5 requests in 1 minute, right? So what will be the probability? Again we will going to use the binomial theorem here. P raised to the power k multiplied by 1 minus p raised to the power n minus k. So what is the value of n here? We don't know because n is infinite. So limit n tending to infinity, nck multiplied by p raised to the power k multiplied by 1 minus p raised to the power n minus k. So now you can see that it is very difficult to calculate. The computations will get very huge, and here we don't have a certain integer values here because n is tending to infinity. Now what we are going to do, we are going to derive our Poisson theorem here, or Poisson distribution here, and the derived equation will be the PMF of the Poisson distribution or Poisson theorem, right? So let us derive it. Again, not equal to px is equal to k. Okay, because now we have to generalize the Poisson theorem. Okay, so we are not putting the value of k is equal to 5, we are just putting the value of k is equal to k, because the Poisson theorem that we have to calculate should be applicable for any values of k, right? So what we have to do now, limit n tending to infinity. Let's first write the equation properly in the terms of lambda. Lambda is equal to average rate, right? Lambda is equal to average rate. So let's write the equation in a proper manner. So nck multiplied by, now what will be the value of p here? The value of p will be lambda upon n. Okay, here also you can see the value of p, what we have put here, lambda was 2 and n was 60,000. So what was the value of p here? Lambda upon n, which is 2 upon 60 into 10 raised to the power 3 or 60,000. Here also value of p is lambda upon n. Why? Because lambda is here too, the value of lambda hasn't changed, and the value of n here was 60. So similarly, since we don't know the value of n, or we can say the value of n is infinity, we are just going to put lambda upon n multiplied by k. Sorry, not multiplied, raised to the power k multiplied by 1 minus lambda upon n raised to the power n minus k. So this is the, you can say the little bit binomial theorem, right? Now what we are going to do, we are going to expand the terms. Limit n raised to infinity n factorial upon k factorial multiplied by n minus k factorial upon lambda raised to the power k upon n raised to the power k multiplied by 1 minus lambda upon n raised to the power n upon 1 minus lambda upon n raised to the power k. So what we have done here, just expanding the terms. Expanding the terms. Now again, limit n tending to infinity. Now what we are going to do, we are going to reduce this form into e raised to the power minus lambda by natural expressions. Okay, let me just make it a little bit neatly here. E raised to the power minus lambda by natural expression. So let's write n factorial upon k factorial multiplied by n minus k factorial multiplied by lambda raised to the power k upon n raised to the power k multiplied by e raised to the power minus lambda upon 1. You can write it in this form also, by natural expressions. So now what we are going to do, just we are going to rearrange the terms so that our computation is easier. Okay, limit n tending to infinity n factorial upon n minus k factorial multiplied by n raised to the power k multiplied by lambda raised to the power k upon k factorial multiplied by e raised to the power minus lambda upon 1 by rearranging. So what we are doing here, we are deriving our Poisson distribution. Okay, so if you are not able to understand the derivation, there is no problem in that. There's no problem for you to understand the next part of this lecture, right? By rearranging, right? Now what we are going to do, we are going to do the limit analysis. Okay, lambda raised to the power k multiplied by e raised to the power minus lambda upon k factorial. So this has been came by limit analysis. So if you analyze the limit very carefully, limit analysis, so this part becomes 1 by limit analysis, right? And this part remains the same. So lambda raised to the power k multiplied by e raised to the power minus lambda upon k factorial. So this is our Poisson distribution. So we can say the Poisson distribution is approximation of the binomial theorem. So when we are going to use our Poisson distribution, when the value of n is very high and the value of k is very low. In this scenario also, you can observe the value of p is very low and the value of n 60,000 is very high. So here we can use Poisson distribution. Okay, value, not k, sorry, p, value of p is very low. So let's use Poisson distribution in this example only. In this example, in which our lambda was, let me write it again, our lambda was 2, our n was 60,000. What are the value of k? Value of k was 5. Value of k was 5. So what is the Poisson distribution that we have just derived? Is equal to lambda raised to the power k multiplied by e raised to the power minus lambda upon k factorial. Okay, so now let's calculate it. What is the value of lambda here? 2, which is equal to 2 raised to the power, what is the value of k here? 5. P of x is equal to k multiplied by e raised to the power minus lambda. What is the value of lambda here again? 2 upon k factorial 5. K is 5 factorial. Now see the amount of calculation you have to perform here and the amount of calculation you have to perform here drastic difference, right? The amount of calculation you have to perform here is very high. I mean, very high. And the amount of calculation here, even my phone can calculate it. Okay. So let me first check. Let me calculate it by using my phone. Let's open the calculator app. 2.71 raised to the power minus 2. Minus 2. Yeah. So if you don't know the value of E, the value of E is always 2.71, right? So here the value of e raised to power minus 2 is 0.13 upon 5 factorial. Now let's calculate it. Now what we have to do, we have to just multiply this by 32 upon 5 factorial. So what is 5 factorial? 5 into 4 is 20. Yeah, 20 multiplied by 3 is 60. 60 multiplied by 2 is 120, right? So 32 divided by 120 multiplied by 0.13. So what is the value of probability here? 0.034. So this is the value of probability, or you can say this is our answer. Right. Again, I am going to tell you when we have to use binomial theorem and when we have to use Poisson theorem. Okay, if in the question of binomial theorem the value of n is very high and the value of p is very low, or you can check the amount of calculation you have to perform in binomial theorem is very huge, as it was here. The amount of calculation you have to perform to get to the answer is very high. Then you can use Poisson distribution. Or in the question, if you found that average rate is given, then the question is of Poisson distribution, right? Now let's do a sample question of Poisson distribution. Okay, I have written the question here. Yeah, let me write the question for you. Consider a request to the web server in 1 second. In past, server has experienced has experienced 2 requests per second. If x belongs to number of requests per second, find p x less than 5. Okay, so the question is in front of you. I recommend you to pause this lecture and at least try to attempt the question. Okay, I hope you have paused the lecture and at least try to attempt the question, or at least read the question, right? So now let's read the question together. Consider a request to the web server in 1 second. So yeah, in past, server has experienced 2 requests per second. So what is the value of lambda here? 2. Lambda is the average. So average is 2 requests per second. If x is a number of requests per second, find the value of p of x less than 5. Okay, first let's write the formula of our Poisson distribution. P of x is equal to k is equal to lambda raised to the power k multiplied by e raised to the power minus lambda upon k factorial. So this is the equation of our Poisson distribution, but we have to find values less than 5. So what we are going to do here, right? We are going to take the help of our summation. So what we are going to do, I is equal to 0 to 4 lambda, not I, k is equal to 0 to 4 lambda raised to power k multiplied by, let me write it properly, e raised to power minus lambda upon k factorial. Okay, some of you, there is a probability that some of you might not understand this. So what this means, we have to find the probability of x is equal to 0 plus probability of x is equal to 1 plus probability of x is equal to 2 plus probability of x is equal to 3 plus probability of x is equal to 4. Okay, so this is the method to solve this question. Let's solve this question also. Let's derive what you can say, let's find out the concrete answer of this question. What is x is equal to 0? Lambda raised to the power k, which is 0. Let's write the values only. 2 raised to the power 0 multiplied by e raised to the power minus lambda, which is minus 2 upon k factorial. What is the value of 0 factorial? It is 1. Not multiplied by, plus 2 raised to the power 1 multiplied by e raised to the power minus 2 upon k factorial. What is the value of 1 factorial? 1. 2 raised to the power 2 multiplied by e raised to the power minus 2 upon k factorial. What is the value of 2 factorial? 2. Plus 2 raised to the power 3 multiplied by e raised to the power minus 2. What is the value of 3 factorial? 6. Similarly, 2 raised to the power 4 multiplied by e raised to the power minus 2 upon k factorial, which is 24. Okay, so now let's do the calculation, the tedious part here. Okay, so let's convert all these fraction in the form in with denominator 24. So this will be what this will be 24 e raised to the power minus 2 plus 48 e raised to the power minus 2, 4 multiplied by 12, again 48 e raised to the power minus 2, 8 multiplied by 4, which is 32 e raised to the power minus 2, and this will be 16 e raised to the power minus 2. If you perform the summation here or sum all these values, it will be 24 plus 48, yeah, so it will be 7 e raised to the power minus 2. So what you have to do is you have to take your calculator. 7 multiplied by 2.71, because the value of e is approximately 2.71, e raised to the power minus 2, which will come approximately 0.95. Let's calculate also. Okay, I might be wrong. Let's calculate. 7 multiplied by 2.71 raised to the power minus 2, yeah, 0.95. so this is our answer to the problem. Now let's discuss about mean and variance of Poisson distribution. In the previous lecture I have covered binomial theorem and I have forgot to cover the mean and variance of binomial theorem, so we are going to cover that also here. So what is the mean of binomial? It is equal to n multiplied by p. What is the variance of binomial? It is simply n 1 minus p, right? No, np multiplied by 1 minus p. So this is the mean of the binomial and this is the variance of the polynomial. Okay, now let's calculate mean and variance of our Poisson. So Poisson is not a different concept, it is just an approximation of binomial itself. Okay, so what was the value of lambda here? Okay, sorry. So what was the value of n multiplied by p in the case of Poisson? Because the values would be same, but the values would be in the form of lambda, right? So what is the, let me write here also, mean of Poisson, Poisson, Poisson. Pardon my spellings. Okay, so first, before calculating the mean of Poisson, let me give you a scenario. Okay, you are tossing a coin, okay, 60 times. Okay, so what will be the average rate of heads in the tossing of the coin? We are assuming that the coin is fair, right? So what is the number of total coin toss? 60 What is the probability of heads? 1 by 2, which is 30. So this is the lambda in the, you can say this is the lambda in the case of Poisson. So how we have calculated lambda? We have taken the value of n, we have taken the value of p and just multiplied both of them. So we are going to do here also. So the mean of Poisson should be n multiplied by p, but we have to put all the values in the form of lambda here. So what is the what is the value of n multiplied by p in the form of Poisson? Lambda. So the mean of Poisson distribution is lambda. Now let's discuss the variance of the Poisson distribution. Variance of Poisson. Poisson. So okay, the variance of the Poisson will be similar to the variance of binomial, because Poisson is, you can say, an approximation of binomial theorem. Okay, so np multiplied by 1 minus p. So what was the value of np here? Lambda. Okay, 1. Now what is the value of p in the case of Poisson? Okay, let us see. Okay, yeah, in this case, okay, in this case, what is the value of p? It was lambda upon n. And while deriving the Poisson distribution, what we are assuming, n equals n tending to infinity. So what will the value of lambda upon n, if lambda is a constant value, and n tends to infinity, so the value of p would be simply 0. What will the value of p? Simply 0. So here in the calculation we can write 1 minus 0, which is equal to lambda. So the mean and variance of Poisson distribution both are lambda here, right? It is pretty fascinating, right? So this marks the end of the lecture. I hope to see you in the next lecture soon.